absorbed or produced when 1 mole of a solute is dissolved to make a solution of a particular concentration and at a specific temperature is known as the heat of solution. 1 or more of a number of complex changes of a chemical nature, such as the formation of hydrates, usually accompany the ordinary physical change of solution itself. Each of these changes is associated with an absorption or evolution of heat also. The summation of all the heat effects of the several changes that occur when a substance is dissolved is evidently what we have called the heat of solution. It thus becomes possible to understand why the solution of a solid in a liquid is sometimes actually coupled with an evolution of heat. In these cases, the heat of fusion of the solid, which is always negative, that is, heat is absorbed, is merely one of several factors in a sum and is overshadowed by positive heat factors from 1 or more chemical changes taking place during the solution process. The solute which we will use in this experiment is zinc sulfate, which has a positive heat of solution. That is, it dissolves in water with the evolution of heat. Assembled on the table are the components of a crude calorimeter. The large beaker is 1 liter in capacity, and the small beaker 400 milliliters. The weight of the small beaker has been determined before the experiment starts and has been found to be 137 grams. A stirrer has been prepared by bending one end of a glass rod into a triangle. The small beaker is now placed in the large beaker. A cardboard disc has been cut to fit into the larger beaker and over the smaller beaker and will serve as a cover. The stirrer will now be inserted through the disc and placed in the small beaker. A second, larger piece of cardboard serves as a cover of the large beaker and will now be inserted on the stirrer. A thermometer is now inserted through the 2 cardboard covers. This thermometer is graduated in 1/5 of a degree so that accurate temperature readings may be obtained. The inner beaker is supported on 3 corks to insulate it from the bottom of the larger beaker. The larger beaker serves merely as a container and screens the smaller beaker off from outside conditions. The apparatus will now be disassembled and prepared for the experiment. First, we must determine the dimensions of the empty small beaker. We will use a small metric ruler and first measure the diameter of the beaker. The diameter is found to be 7.5 centimeters. Next, the height of the beaker will be measured and is seen to be 10.5 centimeters. We will now place exactly 250 milliliters of distilled water in the beaker. And next, measure the height to which the water stands in the beaker. This height is 6.3 centimeters. Knowing the weight of the empty beaker and the dimensions we have just obtained, it is now an easy matter to calculate the weight of the glass actually in contact with the water. This will now be done at the board. You will remember that the diameter of the beaker was measured and found to be 7.5 centimeters. We also determined the height of the beaker to be 10.5 centimeters. Now, applying a little elementary geometry, we can calculate the total area of the beaker, and we find it to be 291.6 square centimeters. The water stood to a height of 6.3 centimeters in the beaker. And again, we can calculate the area of the beaker in contact with the water to be 192.6 square centimeters. The total weight of the beaker was 137 grams. And it's then a simple matter to set up a ratio and to calculate the weight of the beaker actually in contact with the water. That weight we will put equal to X. Well, the weight of the beaker in contact with the water is to the total weight of the beaker, approximately at least, as the area of the beaker in contact with the water is to the total area of the beaker. And solving this equation for X, we find that the weight of the beaker in contact with the water is about 90.5 grams. The stirrer has previously been weighed, and its weight determined to be 31.6 grams. In order to determine the weight of the stirrer in contact with the water in the beaker, we must first determine the overall length of the stirrer. The length of the handle from the top to the triangular base has been measured and is 32 centimeters. The triangular base will now be measured and is found to be 4 centimeters on each side, making a total of 12 centimeters in the base and an overall length of glass in the stirrer of 46 centimeters. The stirrer will now be placed in the beaker. This was done previously, and a red mark has been made on the stirrer at the surface of the water. The stirrer will now be withdrawn from the beaker, and the length of the handle from the red mark to the base of the stirrer will be measured. This length is 6.1 centimeters. And since 12 centimeters of glass occur in the triangular base, we know that 18.1 centimeters of glass are in contact with the water. From this data, it is easy to calculate the weight of glass in contact with the water. The approximate weight of the stirrer in contact with the water may be calculated in a simple and entirely similar fashion. We've measured the total weight of the stirrer, its total length, and the length of the stirrer in the water, and can then set up a simple ratio. The weight of the stirrer in the water is to the total weight of the stirrer, as the length of the stirrer in the water is to the total length of the stirrer. And solving this fraction for the weight of the stirrer in the water, we find this value to be 12.5 grams. We must next calculate the volume of thermometer in contact with the water in the beaker. We have previously immersed the thermometer in the water and placed a small red mark at the water level. In the graduated cylinder, we have placed exactly 6 milliliters of water. We will now insert the thermometer into the cylinder and lower it just to the red mark. The level of the water in the cylinder has risen from 6 to 8 milliliters, an increase of 2 milliliters. We know now, therefore, that the volume of thermometer in contact with the water in the beaker will be about 2 milliliters. We now need to calculate the so-called calorimeter constant, which is the figure which tells us how many calories per degree centigrade are absorbed by the calorimeter itself. We can calculate the weight of the glass in contact with the water because we know that it will be the sum of the weight of the beaker plus the weight of the stirrer. And those two values have been found to be 90.5 and 12.5 respectively, so that the weight of glass in contact with the water is 103 grams. By looking up in our lab book, we find that the specific heat of glass is 0.19 calorie per gram per degree centigrade change in temperature. And then simply multiplying the weight of the glass by the specific heat of glass, we find that the beaker and stirrer will together absorb 19.6 calories for each degree centigrade change in temperature. We have found the volume of the thermometer in the water to be about 2 milliliters. Now, the specific heat of the thermometer bulb is a difficult figure to calculate because both glass and mercury are involved. But again, reference to the lab book tells us that the thermometer constant is about 0.49 calories per milliliter per degree centigrade. And since our thermometer occupies 2 milliliters of volume, we have to multiply that by 0.49 and obtain about 1 calorie per degree centigrade absorbed by the thermometer. The calorimeter constant, then, is equal to the sum of the calories per degree centigrade absorbed by the beaker and by the thermometer, and in this case is equal to about 20.6 calories per degree centigrade. This figure will be used in future calculations as the calorimeter constant. Approximately 12 grams of anhydrous zinc sulfate has been added to this test tube, and the tube and its contents and the stopper carefully weighed. The weight of the tube and contents is 38.12 grams. We will now place the tube and its contents in the water, in the small beaker, in the calorimeter. This is done in order to bring the zinc sulfate to the same temperature as the water. We will now allow this setup to stand for about 15 minutes. The initial temperature is determined by the thermometer and is found to be 28.25 degrees. We will now remove the test tube, dry it quickly with a towel, and rapidly pour most of the powder into the water and the calorimeter. We replace the cover and stir vigorously. The highest temperature recorded is 33.2 degrees. We will now weigh the tube and the remaining zinc sulfate, and we find that the tube and its contents now weigh 25.55 grams. We can now proceed to the calculation of the heat of solution of zinc sulfate. The initial temperature of the calorimeter and the water we found to be 28.25 degrees. The highest temperature which the system reached was, as you saw, 33.20 degrees. Therefore, the temperature change was 4.95 degrees. Now, the weight of the tube containing the zinc sulfate was 38.12 grams, and then this tube, after the zinc sulfate had been removed, was 25.55 grams. So this rise in temperature was caused by 12.57 grams of zinc sulfate added to 250 milliliters of water in the calorimeter. Now, we know that the specific heat of water is 1, so that the number of calories gained by the water equals the weight of the water multiplied by the degrees of temperature change, or 1,237.5 calories, the calories gained by the water. The calories gained by the calorimeter can be calculated if we know the calorimeter constant, which we previously found to be 20.6, and multiply that by the temperature change of the calorimeter. This comes out to be 102 calories. Adding these two figures together, we then have, for the total calories gained by the calorimeter and the water, 1,339.5 calories. Now, this value also equals the number of calories evolved when the zinc sulfate dissolved. And we need then to proceed to calculate the heat of solution of 1 mole of zinc sulfate, knowing that 12.57 grams evolve 1,339.5 calories. This involves a simple ratio. The calories evolved over the weight of zinc sulfate used compared to X calories, the heat of solution per mole, divided by the molecular weight of zinc sulfate, 161.4. And solving this expression for X, we find X to equal 17,199 calories. This is our experimental value for the heat of solution of zinc sulfate. Now, reference to the lab book shows us that the accepted value for this heat of solution is 18,430 calories. Our value was 17,199. The difference is 1,231 calories. Our percent error, therefore, is the difference between the two values divided by the accepted value multiplied by 100, or 6.7% error. And considering the simplicity and almost crudeness of the apparatus, the lack of insulation of the small beaker from the large beaker and so forth, this value certainly is not an excessive error.